this lesson, we are going to introduce complex numbers. Let's investigate the possible solutions to the equation x squared equals 1. We see by inspection that there are two numbers, such that when you square them, you end up with 1. Those numbers are 1 and also negative 1. Can we imagine a number that will be a solution to the equation x squared equals negative 1? Well, no real number can do that, because if you have any real number and you square it, you end up with a positive number, or possibly 0, but never negative. So what if you would like to extend the set of real numbers to include numbers that will be solutions to such equations? Those numbers are called imaginary numbers because they are not real. You can only imagine theoretically such a number that, when squared, gives you a negative 1. So a number with property that, when squared, ends up to be negative 1 will be called an imaginary unit, and this unit will be marked by a letter I. So I represents a number, and this is not a real number, this is imaginary number, defined by the equation I equals root of negative 1, because if I square I, it's like squaring this root, so you end up with negative 1. If we multiply imaginary number I by b, we create numbers that will be called imaginary numbers, b times I, where b is a real number. So how can we see those numbers? Well, we can't see them on one number line. However, if we introduce another number line, which is perpendicular to the first, and will create a Cartesian system of coordinates, you can identify I as a unit number on the second axis, on the vertical axis. So this unit number will be marked by I, however, unit on the horizontal axis is marked by 1. In this setting, a point 0b corresponds to a point that goes b steps on the vertical axis. For example, this point will correspond to a point 3i, that one will correspond to negative 2i. So if a point bi can be located on the vertical axis, and a point a, where a is a real number, can be located on the horizontal axis, therefore a point that corresponds to the ordered pair of numbers ab in the Cartesian coordinate system will correspond to the complex number that will be written a plus bi and will be located in a standard way. So for example, a point 3 plus 2i is located by moving 3 steps horizontally, 2 steps vertically. That's the point. So this is a point on the plane that corresponds to the complex number 3 plus 2i. Any number of the form a plus bi will be called a complex number, with a being its real part and bi being its imaginary part. Notice that if a is a real positive number, then the expression root of negative a can be seen as root of negative 1 times a, which means we can separate root of a from root of negative 1. However, root of negative 1, from the definition, it is the same as imaginary number I. So overall, this will be root of ai. Particularly if we want to see root of negative 4, that will be the same as root of 4, which is 2, times root of negative 1, which is I. That will be the same as 2i. So let's look at properties of the imaginary number I. We'll keep in mind the definition of I. One part of this definition says that I is a solution to the equation something square equals negative 1, which means that I square is defined as being negative 1. Or the other part of definition says I is the same as root of negative 1. So we can refer to both of these. I square equals negative 1, that comes directly from definition of I. Then if we want to figure out the third power of I, we can split I to the 3 into I squared times I, which is negative 1 times I, so overall you have negative I. The fourth power of I can be calculated by splitting I to the 4 into I squared times I squared. That means I squared is -1 times another -1, you end up with 1. And we're going to try to observe the pattern, what's going on with those powers of i's. Will the power of i's produce any other endings, or those are all possible endings? Obviously, we're going to include the first iteration of I, which is just simply I. So we have a pattern I, -1, -I, 1. What will happen if I want to calculate a couple more powers of I, for example, the 5th degree of I? Well, that's the same as I to the 4 times I. But I to the 4, it was already calculated, it was 1. So 1 times I is back to I. The next iteration, I to the 6, is the same as I to the 4 times I squared. I to the 4 is 1, and I squared becomes -1. So overall we have -1. Now you can easily observe that we end up with exactly the same answers as 4 steps before. That means I to the 6 results in the same number as I squared. We can predict that I to the 7 should end up with the same answer as I to the 3. When I to the 7 is I to the 4 times I3. We know that I3 is -I, and I to the 4 is simply 1. So it's just -I. And finally, I to the 8 you get as I to the 4 times I to the 4, which is 1 times 1 back to 1. So as you see, yes, this pattern of 4 different answers, I, -1, -I, and 1, repeats itself, which helps us with calculation because we could actually reduce any 4th power of I because it does result in 1. This could be recorded in the more general way. For example, if you see I to the exponent that is a multiple of 4, I to the 4k, where k is any whole number, we can calculate this by splitting I to the 4k into I to the 4 raised to the k, because power to the power will multiply exponents. However, I to the 4 is 1, and 1 to the k is also 1. So that confirms that any power that is a multiple of 4 of I will end up to be 1. Any power of I that has a remainder of 1 when divided by 4 should be equal to -1. Well, let's see it. We could rewrite I to the 4k plus 1 as I to the 4k, which we already know that is equal to 1, times I. So obviously the final answer will be just I. So we didn't have to really worry about I to the 4k, only the remainder from division by 4 on the exponential level will actually count. It's like I to the 1. Look at the next power of I. This exponent has a remainder 2 when divided by 4, so it's of the type 4k plus 2. As before, I to the 4k, it will be just 1, so it doesn't influence the final answer. The answer actually comes from I to the 2, and I squared ends up to be -1, so we have the final answer -1. As you see, the pattern repeats itself. It's 1, I, -1, well, the following one should be -I. Let's see if that works. Again, let's rewrite this power of 4k plus 3 into I to the 4k times I to the 3. I to the 4k as before is 1, I to the 3 is -I. So we have all 4 possible answers, 1, I, -1, and -I. Using these properties, we can easily calculate any power of I. For example, if I want to find out what's I to the 154, to find out this power, it's enough to divide 154 by 4, which turn out to be 38 remainder 2, and only 2, only this remainder, will actually contribute to your final answer. So you get rid of any full multiple of 4th from your exponent 154, and you compare it to I to the 2, which turn out to be -1. So I to the 154 is actually -1. Now if we deal with complex numbers, we need to be able to add them, subtract them, multiply and divide them. It's a good idea to see the geometrical interpretation of, for example, addition of two complex numbers. Before we identified a complex number with an ordered pair of numbers. For example, here a point a plus bi can be identified with this particular point in a plane, and it also can be identified with the vector that joins the origin with the point. This vector points out to the number a plus bi. If I want to add another complex number called c plus di, it's like adding these two vectors. And adding vectors can be obtained by drawing the parallelogram and the diagonal from the origin till the opposite vertex. So this vector will represent the sum of these two numbers. And when you add complex numbers, you add your real parts separately, so a plus c is the real part of the sum, and your imaginary part separately, so b plus d will be the imaginary part. Well, let's try to add the two numbers that we have given. We're adding the real part of the number, which is 1 plus 1 is 2. And then we're adding the imaginary coefficients. So it's 1 minus 2, it's negative 1, I. Negative 1, we don't have to write the 1, it's just negative I. That's how simple it is. Now, with the subtraction, I will urge you to open the bracket first, so you won't get confused with signs, and rewrite 3 plus 4i minus 1 plus 5i. Now we're adding real parts of the number, which is 3 minus 1 is 2, and then imaginary parts. 4 plus 5 is 9, 9 i's. So 2 plus 9i as the final answer. How do we multiply complex numbers? Well, multiplication is kind of interesting when you look at the geometry of it. It works like that. Number 1 is a real number but can be considered as a complex number. How do we write number 1? Well, it's like 1 plus 0i, right? It's 1 on the horizontal axis but no component of the vertical axis. Let's pick a number that is a little bit closer to the center than 1. It is inside the unit circle. So this distance from 0 to your number will be a little bit less than 1. And that will be your number z, complex number z. If the angle between the x-axis and the ray on which z is located, it's called alpha, this angle will be called an argument of z. That describes the position of z. So if I have the distance from 0 and the angle alpha, I know how to locate z. Now the multiplication of z times z works like this. We multiply the distance of z from 0, which is by the way called magnitude, by itself. We multiply the two distances. So the overall distance of the z square will be located a little bit closer than z by itself, because a number that is less than 1, for example 0.8, will be located at the distance 0.64. So we know the distance. We also need to know in which direction to look for z square. It happens that when you multiply complex numbers, those arguments of complex numbers actually add. So in this case, the argument for one z is alpha and the argument for the other z is alpha. So we're adding two alphas. Therefore, alpha plus alpha gives me the new angle 2 alpha, and that's where you can locate your number z square. When you multiply z square by another z, again, the distance from 0 will decrease, will be a little bit shorter, and the location of z cube will be by rotating from x-axis 3z, because this is another alpha. So that was z cube. If you multiply by another z, it will be one more alpha farther. So this is quite interesting property of multiplication when you look at geometry of it. Let's try to multiply complex numbers algebraically. We basically need to follow the foiling pattern. It's like multiplying two binomials, each term by each. That means you multiply the first by the first, the outside terms by itself, the inside terms, and finally the last terms. Like FOIL, first, outside, inside, last. So to obtain the resulting number, we're looking for those components that will result in real part. The real part comes from first terms, a times c. It will also come partly from the last terms because b times d times I squared turns out back to the real number because it's -1. So it's b times d times negative, so negative bd. To obtain the imaginary part, you multiply the inside and the outside terms because you want to have just one I in the product. So the inside term is BCI, which is here. The outside terms ADI, which is there. So that's a formula that generally describes how to multiply complex numbers. However, in practice, we don't really need to remember this. You just go through the foiling process, and the only thing that you need to remember is that I squared is back to -1, and always convert this at the end. So let's try. 3i times 2 is 6i. 3i times -3i is -9i squared. But then we know that every I squared gives you -1, so that really becomes +9 without I squared. So you start with 9 and then plus 6i. That will be your final answer. Next example, let's FOIL. 3 times 1 is 3. 3 times -2i is -6i. 1 times 4i plus 4i. And finally, -8i squared. So at the beginning, write everything as it is. In the end, when you collect like terms and when you see I squared, just change the sign. So 3 plus 8 because of I squared, and then plus 4 minus 6 is -2i. Now let's add 3 plus 8, which is 11, minus 2i, and that's your final complex number form. You always try to leave your answer in a complex number form. That means a plus bi. First real part, then imaginary part. The next example calls for difference of squares, so it's even easier than the previous. You just square the first term, which is still 1, minus I squared. But I squared is -1 by itself, so you really have 1 plus 1, which is 2. Notice that I multiply two complex numbers and I end up with the real number. It's a good idea to observe how did we get the real numbers by using difference of squares here. This will be needed when we try to factor polynomials in complex numbers later on in the course. And the last example, again, difference of squares that we can use. This is 9 minus 16i squared, which is 9 plus 16, which end up to be 25. Again, real number. The last two examples, we've been actually multiplying numbers that are called conjugates. Generally, any number a plus bi and a minus bi, the numbers that have exactly the same first terms and last terms but they differ by sign, such numbers are called conjugates. And a conjugate of a number a plus bi quite often is denoted by using the same complex number a plus bi with a dash. This dash tells me conjugate of whatever I have here, which means a minus bi. Therefore, to write a conjugate, to write what this number really means, I should write 1 minus 2i. And what that number means? Well, this is conjugate to 2 minus 3i, which is 2 plus 3i. So, if you multiply two conjugates, you end up with a real number. So it's good to record this fact. The product of conjugate complex numbers is a real number. The last operation that we are going to introduce is division of complex numbers. The process of division of two complex numbers is basically the same as the process of rationalization of the denominators. For example, if I want to divide 1 by I really want to get rid of I from denominator, and one way of doing so would be multiplying by I in the denominator, but I don't want to change the value of the original number, therefore I have to multiply the numerator by I as well. And how much is that? Well, 1 times I is just I squared is -1. So overall you have -I. No denominator anymore, this is a complex number, so we did perform the division. In the next example, we have two terms in denominator, and we would like to square the I because that allows us to get rid of the imaginary number. I squared would be -1. But I want to square the I without squaring everything, because when squaring the binomial you would end up with the middle term, which will still include I. So the only way I can do that is by multiplying the denominator by a conjugate 1 plus I, because from the difference of squares, now I'm going to square the first term and square the last term without any trouble in between. So if I decided to multiply the bottom by 1 plus I have to do the same to the top, because then I multiply the original fraction by a factor of 1, which does not change the value of the original fraction. So let's multiply the denominator first by using difference of squares. We'll have 1 squared, which is 1, minus I squared. In the top, copy as it is, because it could possibly be that we can cancel the 2. Since in denominator I have 1 minus -1, so it's 2, then yes, we can cancel this 2. And the final answer is a complex number 1 plus I. In the following example, similarly as before, let's multiply the denominator by a conjugate, 2 minus 3I, therefore the numerator by the same. And in the bottom we keep 2 squared, which is 4, minus 3 squared, which is 9I squared. The top, let's multiply through using FOILing process, so it's 2I minus 3I squared. The next step, because I squared is -1, so this is really plus 3. Start with 3 plus 2I. In the bottom I have 4 plus 9, and 4 plus 9 is 13. So you can leave it that way, but the idea is to actually express your final answer in the a plus bi form. So we can split this fraction into two fractions. First one, 3 over 13. This is the real part of the complex number plus 2/13 I. That's an imaginary part of the complex number. Last example, again, let's multiply by a conjugate the top and the bottom. So 2 plus 3I here and there. In the bottom, as before, we have 4 minus 9I squared. In the top, we can actually perform perfect square formula. So square of the first, it's 4, plus double the product, 12I, plus square of the last, which is plus 9I squared. The plus 9I squared gives me -9, plus 4 is -5, plus 12I, and the denominator becomes 9 plus 4, which is 13. Again, we can split it into -5/13 plus 12/13 I. In the last example, we are going to evaluate quadratic formula -b plus square root of b squared minus 4ac over 2a, given that we have a, b, and c. If those are the values of a, b, and c, my quadratic formula will become -b, which is 2, plus square root of b squared, which is 4, minus 4 times a is 2 and c is 1, over 2a, which is 4. Now we can simplify this. That will be 2 plus square root of 4 minus 8 is -4 over 4. Now the root of -4 is the same as root of -1 times 4. So we can pull the 2 out of the root 4. So we'll have 2 plus 2 root of -1, which is I, over 4. This can be simplified even further if we factor 2 out of the bracket. Now we can reduce 2 with the 4. That becomes 2. So the final answer could be written as 1 plus I over 2, but we would like to have the answer in a complex number form, so we'll separate 1/2 as a real part and 1/2 I as an imaginary part. And the last example, A is 3, B is 2, C is 4. Let's calculate the quadratic formula. It will be -2 for B plus square root of 4 minus 4 times A, which is 3, times C, which is 4. Everything over 2 times A, which is 6. To simplify, we have -2 plus square root of 4 minus 48 is -44. Everything over 6. Now notice the -44 could be seen as 4 times 11 times -1. So root of 4 will be 2. We have -2 plus 2. Root of 11 has to stay, and root of -1 gives us I. Everything over 6. As before, we can factor the 2 to simplify with the 6. So 2 out of the bracket, -1 plus root 11I over 6. That can be reduced to 3. And the final answer in a complex form can be written as -1/3, the real part of the answer, plus root 11 over 3I, that's imaginary part of the answer. And that will be the end of this lesson.